Lesson 8, RAC database monitoring and tuning. And this lesson is a quite long lesson. So I will split this lesson into 3 sections. The first topic will be introduction. And the second topic will be tuning. And third topic will be monitoring topic. After completing this lesson, you should be able to determine RAC-specific tuning component. And even though in RAC environment, it's a good idea to start tuning a single instance, but even after you complete a single instance tuning, if a problem still remains, then you will also have to find out problem area in RAC-specific component. And also determine RAC-specific wait event and global NQ and system statistics. Yesterday, we had a discussion about global NQ service and global cache service. And in order to control concurrency across instances in RAC environment, global concurrency management important. So we had a discussion on this area. And also how to implement most common RAC tuning tips. So this will be second part of this lesson. And then we will get into monitoring topic. So I will introduce some of the important performance pages from Enterprise Manager, and also a brief description of AWR and also ADDM pages. When you diagnose your system, okay, you can actually use some measurement to understand what the problem is. And you can actually go with the CPU time as a good performance measurement, or wait time as another good performance measurement. And if your environment currently running slower, and also CPU time is a large portion of your database activity, as a rule of thumb, possibly by tuning your SQL statement, you could improve performance. But again, this is a rule of thumb. But there are more factors that we have to check. And also, a large percentage of your database activity is wait time, then possibly you will have to look at configuration of your database and your system to find out tuning opportunity. And I want to actually spend some time on CPU time and wait time information. And also, what is the DB CPU time? What is the DB wait time? And also, when you review Enterprise Manager performance page, you will see a lot of, many number of graphs based on average active sessions or active sessions. What are the relationships between CPU versus active sessions, and wait time versus active sessions? And we will have to understand this area a little bit. So I'm going to get into class note. So let's take a look at the first page here. This is to introduce DB time and average active sessions. I'm not sure you heard about database time or not. And this is total database activity time in the given time period. And it is related to average active sessions. So to give you an idea of a DB time, I made this example here. Suppose that we are monitoring 5-second database activities here. So we have a first second time period, and second, and third, and fourth, and fifth. So we have a 5-second the time period. And over the 5-second time period, we observed 5 sessions, for example. Okay, this is just an example. And also, you can actually interpret this graph in this way. Session 1 logged in the beginning, And then green color line, assuming that this is a CPU time. I just made an example this way. So first session issued a SQL statement and performed certain activities. And by spending 1 second the activity time. And then it had to wait another 1 second to complete operation. So this session performed activity in the 5 second time period. So this session activity time is 2 seconds. 1 second CPU time, 1 second wait time. And then second session logged in as well. And this session consumed the 4 second database activity time. And 3 seconds is a CPU time, and 1 second is wait time. I'm just making an example. And also, third session logged in, it consumed the 2 seconds over 5 second time period. And also, session 4, it consumed the 2.5 second time period, 1 second consuming CPU, 1.5 second waiting for some certain resources. And also, session 5 also logged in. And then this session performed the 4 second database activity, and 1 second CPU activity, 3 seconds is wait time activity. So over the 5 second time period, we had 5 active sessions. Okay? So we have some good information that can be derived from this example. Over the 5 second time period, what was the total sessions activity time? So in this case, 2 seconds plus 4 seconds plus 2 seconds plus 2.5 seconds plus 4 seconds. The total is database activity time. And this is called DB time. Okay? And also, you observed 5 second time period. That is, it elapsed the time. So when you compute this, and you will get one value. And this value is called average active sessions. Meaning that if a DB time goes up, your database activity time goes up, then your average active session goes up in the given time period. Because of this reason, analyzing your database activity by average active session is also same analyzing your database activity by using DB time. So many of enterprise manager performance graphs showing you average active sessions, meaning that by analyzing your database activities through average active sessions, you can also analyze your total database activity time as well. So when you look at this, so we have actually some information here. So your database activity time, according to this, total was 14.5 seconds. This is your DB time. Okay, that's your DB time. Now, I want to analyze this DB time by performance measurement. So there are two possible things. I can analyze my database activity time by wait and also by CPU. Okay? So if this were problem time period, and you should analyze this database activity, and we use two tuning measurement. One is wait, and one is the other one is CPU. So from this example, you can analyze your database time based on this analysis. We learned that 6.5 seconds was a CPU time out of 14.5 seconds. Okay. And also, about 8 seconds, so for 8 seconds is wait time, meaning that your database is a wait dominant system. If this is a problem time period statistics, by eliminating wait, you have an opportunity to tune your database. So as you can see, we're going to actually use a top-down analysis. So you actually take a look at DB time, and then you analyze it by wait time, and you analyze it by CPU time, and then you actually look at further. So you can actually analyze your database activity time in this way. So that's in the meaning of a CPU and wait time tuning dimension. So since your database activity time is DB time, and this can be analyzed by CPU and wait, and during the problem time period, okay, what is actually the top issue, CPU or wait? And you can also drill down even further. RAC-specific tuning area. The rule of thumb is, in RAC embodiment, if you observe a performance issue, go with a single instance first. Because in many cases, the problem is a localized problem. Okay? So if there is a performance issue, take a look at a single instance, and then find out the problem and tune. Now, even after you tune single instance, if a problem still remains, then you may want to get into RAC-specific area. And here are the RAC-specific tuning opportunities. Instance recovery. And we learned the instance recovery topic. If instance goes down in RAC embodiment for a short amount of time, your database is not available because your cluster is frozen to redistribute RAC metadata, global cache service metadata, global enqueue service metadata. But actually, this instance recovery tuning is not a major part, and this is not common. I showed you an example through alert log file. So when I stopped or crashed one of the instances, the peer instances had to work together to reconfigure instance, and reconfiguration time was less than 0.2 seconds. So instance recovery time is a sub-second. This may not be a major and common issue in RAC embodiment, but it's a good item to understand. And also, interconnect traffic. As part of a practice activity, you will generate workload, and also you will make block transfer, and you will see the performance issue mainly caused by excessive block transfer. Okay, so theoretically, if you are connecting in the RAC instances over gigabit Ethernet, so we can actually transfer the data blocks at rate of 100 megabytes or 120 megabytes per second. So most of embodiment in a gigabit Ethernet is more than enough. Or you can use a NIC bonding, or you can use the InfiniBand as an interconnect network. Okay, so there is a way to check data traffic through multiple instances in your embodiment just by looking at Enterprise Manager. So you see that whether your interconnect hardware is enough to support your current traffic. If it's not, you have to find a way to reduce block transfer or upgrade your interconnect hardware. And also point of serialization. That's another thing what you have to take a look at. In the cluster embodiment, in RAC embodiment, we will have to manage it concurrency globally. So sometimes your local session may have to wait, maybe because of a remote session or a remote instance. Or if there are concurrent, concurrent access to a resource from multiple instances, that may cause another problem. So that's what you have to take a look at. We have a few examples. And in order to diagnose your single instance in RAC embodiment or RAC-specific area, we can use wait event and also system and enqueue statistics. And also we can leverage Enterprise Manager performance page, and you can also review AWR report. If an AWR report is not available, you still can use the stats pack as well. So let's take a look at analyzing cache fusion impact in RAC and the cost of a block access. Now let's take a look at this. I'm going to give you this information. Suppose that you have a single instance database. So I have a single instance here. And we have a database block in memory here. If this were a single instance environment, how long did it take to read this database block? This is just a millisecond and less than a millisecond. Okay? But what about in RAC environment? It may take longer than this time. Why? Because of a cache fusion algorithm. Because there are more processing that must be complete to be able to access the database block. So yesterday, as a part of lesson 7, we had a discussion of a global cache service and also global enqueue service. Your resource must be managed globally, and also concurrency must be managed globally. So because of that region, there is a little bit of overhead, even though there is minimal. So for example, in lesson 7, we had this discussion, if you remember. So, and this is in our example. I will just review again. So this is an example of a two-node cluster, ORCL1 in the left-hand side, ORCL2 in the right-hand side. And also, we have a global resource directory across instances, especially part of a shared pool. And also, in the global resource directory, we keep metadata for global cache service and global enqueue service. And suppose that this is a global cache service example, okay? And 2 blocks owned by instance 1 and 2 blocks owned by instance 2, okay? So from session 1, I'm looking for one database block here, and this database block owned by second instance, for example. So what does this session do? This session must work with LMS process, global cache service background process. So I need, certain block, and who should I connect? So LMS, it will check global resource directory information like this. And if a block requested was a number 12, then we can easily check ownership. So ORCL2, second instance, is owner. So what LMS does, since LMS in the instance 1, it cannot modify metadata of a block number 12 because its ownership is a second instance. Because of this region, LMS work with remote LMS. And then remote LMS will check the status of a block and update this metadata and return it to local LMS and transfer this block back. And then we are able to access the database block. So as you can see, the cost of a block access, this includes global cache service statistics and also wait time. So I'm requesting block, and to get this block, we have to go through multiple processes, and then we will have to wait until block is delivered. So response time for cache fusion transfer is determined by IPC protocol, so inter-process communication, and then between LMS process communication, and then your block and messages are delivered back to a requesting instance over the network. And these are part of response time. So your block access time, it's not like block access time in the single instance database. Even though it's very minimal, there is something what we have to take a look at. And response time is not generally affected by disk I/O factors. And this is a typical latencies for RAC operations. So let's take a look at this area. When you look at this, average time to process consistent read block and also to receive it. So your server process requests consistent read block. So we know what is the meaning of a consistent read block, right? So one session, update a record, or insert update a record in the block. Before commit, another session requests the data that is being committed, or data that is being updated. Then the consistent read block must be created to provide the consistency to second instance, a second session. So, to request the consistent read block, server processor work with LMS process, and the typical time range is this 0.1 to 10 millisecond. Mostly I see this area, 0.1 millisecond, so more towards to a lower bound. And also after request, and then the message must be processed, and then block will be returned back to requesting instance. So to receive this block, it may take this amount of time. But most likely this is a more common observation. Okay, so from typical to lower bound, this range is better than physical I/O. So even though we have some extra processing, it is still better than physical I/O. Okay, and upper bound is also about same as the physical I/O, but mostly you will see typical to lower bound. Now, if you request a block for DML, I need the most current block in the requesting instance. So in order to process, it takes about this amount of time. But in order to receive it, it takes a little longer time. Okay, so 0.3 to 30 milliseconds. So as a rule of thumb, mostly you will have to see around this range, lower bound to typical. Okay, for short amount of time, if latency around this range, that's acceptable. So around 10 milliseconds for consistent read block receiver time, around 20 to 30 milliseconds for current block receive time. So if you observe for short amount of time in this way, that's acceptable. But you observe typical you observe a latency greater than this upper bound constantly over for a long time period, then you have to find out why. And how do I know your current the latency for RAC operations in your environment? So we can take a look at current block statistics here. So this is a consistent read block, and this is a current block time. And we have a consistent read block receiver time, and also current block receiver time. It's less than 10 milliseconds. So it's just still better than physical I/O, even with the cache coherency operation behind the scene. So it is acceptable. But sometimes if it goes up to 30 milliseconds or 40 milliseconds in the statistics time period, AWR snapshot time period, then you have to find out why. Is it because of a remote instance? Is it because of your RAC interconnect configuration issue? And what is the issue? So you will have to take a look at interconnect area to have a tuning opportunity. And also, we can leverage wait event to understand RAC operations. Sometimes the customer misunderstand wait event is bad. But in reality, wait event is not bad. Wait event, it only gives you an idea, okay? Because to describe in each Oracle operation, Oracle uses wait event. For example, so if you actually wait for completion of a direct path I/O. So for example, I'm doing full table scan. As a part of it, we are reading data directly from disk and cache into the PGA. So to complete this operation, I have to wait. Then in order to describe this activity, we use a wait event called DB direct path read, wait. Or I have a random I/O request as a part of index scan. I'm reading single block from the disk and cache into SGA memory space. And to describe this activity, Oracle uses DB file sequential read wait. So these are all normal wait. Just like in a single instance environment, and even in RAG environment, there are same set of wait plus additional RAC-specific wait event. If a performance goes bad in your embodiment, then you may want to compare wait event and its wait time. So if you have a same observation, same set of a wait event from good time period and bad time period, then what you have to take a look at is, wait time. Okay, normal time I only had to wait 2 milliseconds to complete I/O, but now I have to wait 50 milliseconds. Same wait event, but why? We had to wait a lot longer time, and that's analysis. So wait event help to analyze what sessions are waiting for. In RAC embodiment, there are two types of a wait event. One is a placeholder wait event while waiting, and precise event after waiting. So initially, when a RAC session requests one resource, and this session doesn't know, how long it takes, how it can request the resource. So until operation is done, Oracle will simply use placeholder wait until requested job is done. And once job is done, your placeholder wait event is converted to actual wait event. And that gives you more meaningful description of operation that was done. And also, global cache waits are summarized in a broad category called cluster wait class. And these wait events are used in ADDM to enable cache fusion diagnostics. So here are the $3 views that you can use to view a total wait event. So total wait event for an event from $GV sys event, and wait for a wait event class by a session, and also wait for an event by session. So you can actually use different views to get wait event related information. And here are the examples of global cache wait events in RAC embodiment. So here we have a couple of things here. So let's see here. And this is a placeholder wait event. Global cache, the current request, and multi-block request. So actually, it's more than that. What I'm going to do, let me copy this. So let's take a look at this. In order to save space, we actually made this example in this way. Actually, this gotta be like this. And it is an example of a global cache, current block request. That's a one wait event. And also global cache consistent read block request. And this is another wait. And also global cache multi-block request. And these are all actually this is the same thing. Global cache consistent read and also current multi-block request. So we have actually multiple requests related to waiting. So that's a placeholder. So we don't know how long we have to wait. So I'm requesting current block, but I don't know how long it will take, where I can get current block. And also I'm requesting consistent read block, but I don't know whether I'm going to get this block from remote instance or from the disk. I have no idea. So until job is done, request, which is a placeholder wait, will be reserved, and this will be used until job is done. And once job is done, and you will see these kind of precise wait events. So in this example, global cache, current, and consistent read block, two-way and three-way. Idea is very simple. This is actually this case. Suppose that you have a 3-node cluster, and we have a master instance here. and we have a requesting instance here. Okay, so requesting instance request block. If the block exists in the master instance, then we can receive this block directly. So we are able to receive requested current block or consistent read block by working with the two instances, requesting and master instance. Okay? However, the block that I requested is not in the master instance. However, I had another instance here. So, I can get this the block by going through the instance that currently holds the block requested. Then we have to work with the three instances: requesting instance and master instance. Instance currently holds block requested. So this is a three-way communication. Now, when you look at description here is block requested received after working with 2 or 3 instances, and this is a keyword, immediately after request. So I requested the resource, I was able to receive a resource immediately, meaning that just like a disk I/O wait, and this wait event is normal in RAC environment. Okay. Now another one is global cache, current and consistent read block ran two-way. The idea is we have a 1, 2, 3 node cluster. Okay, and data requested by requesting instance is in the physical disk. So this is a requesting instance, and this is a master instance, and this is another instance. So requesting instance request block owned by master instance. However, the block doesn't exist in the master instance or other instances. Now, if a master instance must read this block and cache it and deliver this block to requesting instance, then this is too much expensive. That's why, in order to simplify this process, master instance only return message. Okay, I'm going to give you grant, meaning that permission. I will give you permission, and you directly access the block and read it from the disk. So that's in a faster way. So, when you look in a description here, not received and not mastered locally, but requesting instance was able to receive grant immediately. So that's another the normal wait event, but it only gives you this kind of the information. And the other one is consistent read block congested. That's another one. So what is the meaning? So meaning that LMS process wasn't able to handle requests as quickly as possible. For example, so I have a requesting instance, I have a master instance. And global cache, so we are working on global cache. Global cache request, it is handled by LMS process in each instance. And it uses queue, okay? So, global cache request may be handled by local LMS or maybe remote LMS. So suppose that, session connected to instance 1, and then, requested a resource, and then resource owned by remote instance. So, LMS will work with the remote instance, and then request will be enqueued in the request queue, because this LMS may have to serve multiple requests from multiple instances. Okay, the congested means LMS was so busy, so we were not able to dequeue this message to handle. Okay, because of a CPU bottleneck, maybe not enough memory because of a swapping is going on. So there could be many reasons. So in that case, you will have to take a look at a host level resource availability and why that happens. Is it because of a lack of a CPU? LMS is already running with the highest priority. So starting more LMS, it may not give you a better benefit. So you will have to diagnose a server to see why LMS doesn't respond properly on the timely manner. So that's what you have to take a look at. And another one is we have global cache block busy. That's another example. So as you can see a description here, block was received but not sent immediately. So requesting instance wasn't able to receive block requested immediately. Why? Because of block busy, because of internal operation. Block was busy because of internal operation. So in which circumstances you're going to see this example? Think about that. I have a one instance 1. I have an instance 2. Okay? And I had a one session connected to second instance. And then this session worked on this block with exclusive current buffer state, meaning that this session was requested this block for DML and then modified this block. Okay? And also, from session 1, shortly after and before the commit, session 1 requested the same block as a part of another DML. Okay? So this time, requesting instance work with the remote instance and asking for this block. Because a change was done, but even though it is before the commit, so what happened is, internally, in order to transfer the most current block back to requesting instance, there must be something going on. There must be something done internally. For example, a redo that describes changes made to this block must be written to disk. Redo operation. Okay, flushing redo must be done. So until this internal job is done, this session must wait. And eventually this block will be copied over to here, and then I can do another operation. The block that was current, it becomes a PI block, pass the image. Okay, so this session is waiting until this job is done. So it's because of concurrent transaction through multiple instances. So internal job must be done. So you may have to check concurrent transaction across instances if this is a major issue. And another thing is global cache current grant busy. That's very similar. So we know actually what is meaning of a grant. So the granting message was delayed. And also we have a global cache buffer visit, meaning that in this example, in order to complete internal operation, this session waited. In addition, if multiple sessions look for same block, which is a hot block, like a block header, okay, or in a segment header block or index of blocks, then because of a hot block, buffer becomes busy. Okay, so that's also another example. So you have to find out way to reduce the buffer level contention and also failure. So this kind of actual wait event will give you some description of event in your environment. So most likely this is good and this is good, okay. But if you see this kind of a wait event and this is a good tuning opportunity, so you will have to drill down further if this is a real problem from problem time period. So you will have to leverage support node to see whether there is any known issues And also, you will have to take a look at your server resource availability, and there are many things what you have to check. And also, we have NQ-related weight. NQs are synchronous, and NQs are global resource in RAC. And these are all the most current in a global NQ weight, TX and TM. So that's transaction logs, and undo-related logs is here. Log is here, and high watermark related, and also we have a TA log and sequencer-related logs. So we have all global NQ-related weight information here. And you can view statistics information in RAC environment by using GV$view. And also from GV$view, you can see global cache service statistics, and also global NQ level statistics, and also statistics for messages sent. And before looking at GV$view, it's a good idea to use Enterprise Manager to get an idea first. Okay, this is for part 1 of lesson 8. I briefly introduced the RAC tuning. So RAC tuning introduction was a part 1.